Good evening, everyone. Tonight is another episode of Dan Does Data, and tonight we're coming back to a roots, something we've done before a little bit, where I just work line by line through some existing example and try to explain what the heck is going on while it's doing it. Sometimes this works pretty well, sometimes it just strains my voice a whole lot. So if you go to the Keras GitHub page, fshala/Keras, and you look in the examples directory, Keras/examples, you find a whole bunch of various examples for some of the more popular machine learning tools. So you'll see a bunch of examples related to MNIST, the digit classification. You'll see a bunch of examples related to IMDb, like trying to classify movie reviews, things like that. You'll see this Deep Dream example and other stuff like that, and a whole bunch of other things. So I've definitely used these quite a bit to just understand what the heck is going on. So I thought it would be good to just walk through one or two or however many of these and just sort of explain line by line, as the name of the series is, what the heck is going on. So I haven't decided which ones I want to do yet, so I'm just going to pick one. Let's call it MNIST sklearn wrapper.py. Boom, let's go there. So build simple convolutional neural network models on MNIST using sklearn's grid search CV. I'm not 100% sure what that is. Let's get the raw. I just want to download this particular file. Save page as. Yes, that is what I want. sklearn wrapper. Doink. So I don't actually need that. Let's move from downloads, sklearn. Nope, that's not it. Yeah, there we go. MNIST sklearn wrapper. Just move that locally. So on the left, we're going to execute it a little bit by a little bit. And on the right, I'm just going to walk through what I believe each thing is doing. So it looks like the overall goal of this is to build a convolutional neural net model to classify digits, but we're going to build several models, and we're going to use this grid search CV thing to find out which model is the best. So we're going to have some landscape, a whole bunch of models, and grid search CV will hopefully describe what the heck is the best one. Can we go through a question from the audience? Can we go through the models of Keras contrib? That'll be something I'll definitely look at. I'll keep that in mind because I might get tired of doing these official examples. And Keras contrib contains a whole lot. Let me do one thing. Let me fix the color here. Much better. Okay, let me just start right at the beginning here. So this first line, if you're in Python 2 land and you want to have a print function, such as print4, whatever, to have the proper print function, you should do that. Otherwise, you'll think, I can do print4. In Python 3, you cannot do that, though. Python 3, you don't get that kind of print. So by doing from future import print function in Python 2, you get the normal kind of print. And you might even get things where you can say print for file equals, and like whatever the file handle is, usually F. That's after you've done some sort of with open some string R as F. Something like that. I'm in Python 3, so I don't need to worry about that. This line, of course, we want to import Keras just to have access to all the Keras subcomponents. Those ones that we'll be using quite a bit, we will import directly. Yes. Datasets. So Keras comes built in with several datasets. Oh, you're going to see some annoying garbage on the left because the ano got weird, but don't worry about it. Everything is fine. Don't worry about it. Everything's fine. Yes, I definitely should have done that ahead of time. If you're going to suggest use TensorFlow instead of Theano, don't bother. It doesn't work with my device. It doesn't work with my GPU. Theano isn't very good with my GPU, but it does work. So in Keras, there's a whole bunch of built-in datasets. And by whole bunch, there might be like 5, 6. Boston Housing, Sci-Far, Sci-Far 10, Sci-Far 100, IMDb, MNIST, and Reuters. Reuters News Service. So you get access to built-in datasets. And by built-in, I mean that it's more like it goes out and downloads the datasets for you. Because if you say mnist.get file, load data, what does this do? Path where to cache the datasets locally. So it'll go and do it once. So .keras/datasets. That's a good question. What is in my .keras/datasets? Yeah, so I've already downloaded MNIST in this apparently Numpy format and a pickle format. Who knew? So when I go to load data, it'll already have downloaded it and won't take very long. And I believe what it just does is check, hey, is this file there? And if not, get file, path origin. So it will download it if you don't already have it, and then load it, and then put it in the training and testing data. But this is just doing the import. Okay, sequential, we're going to be building models with sequential. That means we're going to have models that in general take some input, give you some, do something into one layer, and then pass that output into some other kind of layer, and so on and so forth. It's just a linear sequence of things until you get to the output. This is distinct from, let me open up GIMP actually. Oh, that's not what I wanted. Briefly try to explain this. You can have models that are general graphs instead. And I know I've probably said this before, but the whole point of this is to be kind of self-contained and simple. That's fine. So you could, as I said, have something, and another thing, and another thing, and another thing. And let me drain the size on this. That's just a sequence of different layers. You could, however, have some kind of input over here, and especially if you've got different kinds of input, like images, and then maybe some floating point values, and you do a couple things over here, and a couple things over here, and then at this point, you want to bring your other stuff in. And then maybe I want to compute some stuff over here that has to do with one set of numbers and some other stuff over here. Like if you're driving a robot, maybe you say, oh, go this direction and go this fast. So that's a general graph construct. And you'll see this called the functional model. The functional func. And the simpler one is the sequential. Doink. So this is just relatively simple models. In general, use the sequential model unless you need to use the graph model. It's going to save you a lot of typing and a little bit of headache. That's what I suggest anyway. Okay, the next line. I feel like this goes slow, but we work through everything exactly. These are some of the most common layers we're going to need. So, dense is the standard densely connected neural network. Question from the audience, how long am I streaming? I stream for an hour. Hour at a time, because my voice will give out otherwise. And I'll be back next week. You can hear more of my beautiful sonorous radio voice. So dense is a fully connected layer in a neural network. So at some layer, wherever you are, you've got a bunch of numbers, n0, n1, n2, n3, whatever, that are just sort of in a vector, in a one long array. Dense says, hey, take each one of those numbers and multiply them by some weight, sum that up, and put it through some other function, which we'll get to later. And in a dense layer, you're saying, I want to do that like p times or whatever. So I want to have p weights for every single input. And I've connected all of my inputs to that layer, these n0 through n whatever here, all my n numbers. I've connected each one of those to my p outputs. And so it's considered to be densely connected. That's what dense is about. So that's the standard thing to do. If you're doing like linear regression, you're only computing one output number in a sense, but you've computed a weight for each one of your inputs. So that's all dense is. Dropout, this says during the training phase, keep only a fraction of those nodes, those p nodes, at any given layer, so that no given node can just sort of memorize things. Sorry, there's a spider crawling my camera. Very scary. We'll get more into that as we go into the models. Activation, this is that nonlinear function that you shove your weighted sum of inputs through. So this is going to be a variety of different things. We'll get into that, what they could be as we get to them. And flatten, this is a special kind of layer that takes input that isn't just a vector, but in fact is a two-dimensional array, and it just, whoa, one second. Let me make a new one. Oh, no, cursive. Do, there we go. It takes a 2D array or higher, say 3D, 4D, whatever. So you've got some numbers here, and a bunch of rows, and a bunch of columns, and it just sort of unrolls that into a one long vector. That's all. That's all flatten does. And so this often happens when you have images as input, and you compute some two-dimensional based function on them, and then eventually you've got some weird two-dimensional intermediate value, but at the end you sort of need one number, and you don't really care about the structure anymore, so you flatten. And stupid things in the way. There we go. Nope, god dang it. See, I don't know why. Fine. Toolbox, you can live down there. Perfect. That's great. So that's flat. Some of those other layers we're going to need, these could have been in the upper level, but I guess they didn't want to be. Rather than dense, you can have a convolutional layer, which says, I want the weights. I'm only going to look at a few of my inputs at a time, a few that are structurally related. That is, if I'm looking at a two-dimensional grid, these will be pixels that are near each other, that are in some window, some square. And I want to compute some function on that square. So you're sort of doing a little mini dense layer on just that square. But then you take your square and you slide it over a little bit. And you compute the same function with the same weights, but just slid over. And then you slide it over again. That's called a convolution. Max pooling is very closely related to this. It says after you do that convolution, you compute some value. Now you've got like a whole image, essentially a bunch of pixels of values, effectively. And you say, you know what, I don't actually care what all the explicit values are, I only care what the biggest value in some local neighborhood is. So you'll often look at little 2x2 groups of these convolutional outputs, and you'll say, alright, well, which is the biggest one in this group? Okay, then move over 2, and you got some new 2x2 group, and you say, oh, just keep the biggest one. That's maximum pooling 2D, so you're decreasing the size of your data, and hopefully you're pulling out the most interesting features. Okay, this line is new to me. This is keras.wrappers.scikit-learn import keras classifier. So scikit-learn is a machine learning package that's designed to be like brain dead simple to use, and it comes with a lot of common, very like classical machine learning techniques. You'll see like linear regression, logistic regression, a lot of other things in there. It's probably not made for production level work, but if you're just trying out ideas or just learning, it's really super useful. But I wasn't even aware before today that there were wrappers for it in Keras. Scikit-learn. What is this? Not found. Okay, let me see if I can import this. I'm generally opposed to, see, now it's there. Yeah, whatever. I like being able to just poke around and dot whatever, dot whatever, dot whatever. This is not informative, and tell me what this is. This is a base wrapper. Keras scikit-learn wrapper. Should not be used directly. Use descending classes instead. Alright. So I suspect this will be used. Implementation of scikit-learn classifier API for Keras. Once we've created some Keras model to wrap it in the sense that sklearn can use it, and whatever tools from sklearn can run, it will be able to use. That's what I think anyway. What's going on here? So arguments, array-like shape, number of samples, number of features. So how many data points do we have? How many input features do we have? Test samples, rand samples, number of samples, yada yada yada, and other dictionary arguments. Predictions, array-like. So in this particular case, we're trying to classify, so we're going to get a probability for a given data point. We're going to get n probabilities. We'll say what's the probability class 0, what's the probability class 1, what's the probability class 2, yada yada yada. Those 10 or n probabilities ought to sum up to 1. And that's sort of what we're getting at. Okay. This line here from Keras import backend as k. So if you're using TensorFlow or Theano, that's the backend. And this will sort of give it to you directly. And k. So things that are particular to TensorFlow or Theano will be involved in here. And this line, this grid search CV, this is what's going to select between models. And I don't remember exactly how grid search works. I suspect if your space, let me go back to my GIMP picture. If your space, no, bring GIMP. God, turn it. Do not know why GIMP is broken. This is so dumb. Layers, brushes. There we go. Okay. Yeah, I don't know why the Ubuntu GIMP business here is trouble. Imagine if you've got some two-dimensional space of parameters for your model. Maybe as like number of nodes and I don't know, maybe number of layers. Something stupid like that, or the learning rate, or whatever. You're just going to say, all right, well, I can't sample every single point in between, like because the learning rate is a floating point value, and maybe I'm willing to consider up to 512 nodes, and that's really too many for me to think about. Running all 512 times, I don't know, 100 different learning rates models. So you say, all right, well, let me just suppose that an answer that's close to my answer will be pretty good, and ones that are closer to the correct answer will be more right than others. So build a model, assuming, I don't know, maybe this represents one node and learning rate of 0.001. And then come over here. Then you build another model. Now we've got 2 nodes and the same learning rate. And then you make another model, and this is 3 nodes and learning rate of 0.1 or whatever, and so on and so forth. So you do all the n different kinds of nodes. So however many you've got here, maybe you're willing to try 10, whatever, and you're willing to try 10 different learning rates. You do those, build all 100 of those models, and then you should be able to look what is the best one. I believe that's what grid search is doing. It might mean doing some locally and then doing some other ones. Let's search. Let's do a grid search on grid search. Grid search CV. Exhaustive search over specified parameter values. Oh, okay. So it's exactly what I said. So in this case, our score is going to be train the model and see how it does, probably on some kind of validation data set. But the idea is we're going to search over some space of parameters that we're willing to consider, and it maybe in the real world, the answer is like here between some parameters, but we'll get pretty close by doing this one because we will have guessed that. And then from there, maybe as a human being, we can look at that and say, oh, well, let me try this other stuff. And you'll be able to see what the score, how that evolves over the space. You should be able to plot like a 2D plot like this. Maybe it's n-dimensional because you've got n-dimension things. Who knows? Yeah, brushes, you could stay down there. Toolbox, you can stay down there. I don't know why you're over there. That continues to irritate me. Mystery. Anyway, but that's with you have to get sklearn to use that. I happen to have sklearn already installed, so it saves me some trouble. N class is 10. We're trying to classify images of digits. So there's 10 digits. That's how many classes we have. These digits, they come in images that are grayscale, and they're 28 rows by 28 columns. So it's a relatively small image. You'll note 28 times 28 times 28 is 784. Another question from the audience. In the convolution, if the input tensors are 32 by 32 by 3, and the filters are 3 by 3 with depth 10, I assume depth is filters? How many filters are made? A little confused about the weight sharing. So yes, if it's 32 by 32 by 3, there's 3 channels, like red, green, blue. And your filters are 3 by 3, so that's your window size. And you're saying the depth is 10, so you've got 10 sets of weights, is what you're doing. You're going to have 3 by 3 by 3, in effect, because you've got 3 channels. So 27 weights for each set of your weights, for each kernel. So you'll have 27 times 10, you'll have 270 weights plus 10 bias terms in that case. Assuming you're sliding by 1. Well, that doesn't even matter. That's how many weights you have. Okay. Now we're actually going to load the data. We briefly looked at this function. It returns your training data set. I guess the Y is what we're trying to predict the classes. It'll be easier when I show you. So this doesn't have a shape, does it? No, well, it does. Our 60,000 training samples, each of size 28 by 28. and Y train is 60,000 outputs, and this is going to look like integers. So this just says, hey, the first one is a 5, the next one is 0, whatever. We don't get probabilities for each one because we just know exactly. Okay, that's that. If k.image data format, let's look at what k.image data format is. Channels first, it is. So this is just shifting around the channels. If there were colors in our image, you'd need to be very careful about this because Theano and TensorFlow store these differently. Sometimes, not always. I've gotten burned by this before. Either way, let's run that. And all it's really doing, since I promised I would go line by line, in Theano universe, I think, in one universe, this one here, this represents sort of how many input colors you have, or channels, if you can imagine red, green, blue being your channels. That comes before the actual image size when it wants to get stored. Whereas in the other one, which I think is TensorFlow, the image size comes first. This image rows, comma, image cols. That's all. That's all this is doing. So it's changing the input shape. In our case, it doesn't really matter since there's only one channel. If you set up your model correctly, it wouldn't matter at all. Okay, xtrain is currently stored as uint8s. That's an unsigned 8-bit integer. So it can only take on 256 values from 0 up to 255. So it's sort of if something is 0x0, if that's the value of the byte, versus 0xff, the maximum value. We prefer to deal with floats in the machine learning universe. So we're going to say, hey, change the data type to 32-bit floats. So give yourself a little bit more precision. There's still values that are between 0 and 255. If I say numpy.max of xtrain, if I import numpy as np first, you'll see this. It's still 255.0, comma 0 for Europeans, I guess. However, we're going to rescale everything to be between 0 and 1. So you divide by 255 here, because the maximum value is 255. So what was the biggest value will become 1. What was the smallest value, 0, is still 0. So if I do this again, 1.0, no problem. Okay, now we have a nice little tool here. Keras gives you utility to convert your integer labels at 5, 0, 2, whatever, into an array of probabilities. Now, of course, we know which one's the correct one, so the probability of the correct one will be 1, and the probability of all the others will simply be 0. And this will make our computations a heck of a lot easier when we build our Keras model, because we're going to be predicting 10 probabilities for each data point. And we just sort of want to bang that against our actual ones to see how correct we were. So if we predict 0.99 for the correct value, then it's sort of 0.99 times 1.0 is very good. Whereas if we predict 0.1, then it's 0.1 times 1.0 is not as good. And you sort of don't care what the distribution is on your wrong answers. You can debate whether that's correct or not, and that's how you determine your loss function. In this case, we don't care what the wrong ones are. We only care what the right ones are. So 2 categorical is just a convenience function to do that for you. And if you look at Y train now, you'll see you get a bunch of. Well, let me show you the first guy. The first 2. Can you do that? Yeah. So this is the first vector, the first data point. We've got a 1 in the 5's position. 0, 1, 2, 3, 4, 5. The next one was 0, so we put a 1 in the first position. 0, 1, 2, 3, 4, etc. And you go on down the whole way. And we do that for the testing data set as well as the training data set. Okay, now we're going to make some models. So these are the various kinds of models that we're going to be doing our grid search over. Creates model comprised of 2 convolutional layers followed by dense layers. So we'll do some of this convolutional windowing. I have some other videos up if you want to learn way more about that. I don't want to spend a ton of time on that. And then it will flatten out the model and then do a dense layer and finally compute the probabilities for the digits. And so this function, it just says, how big do you want your dense layers to be? Filters, how big do you want your convolutional layers to be? Kernel size. Convolutional kernel size. I think this is the window size, essentially. And pool size, how big do you want your pools to be? So we've got like a four-dimensional space. But it's bigger than that, really. Because the filters... So filters gets reused in two places. Down here. This first convolutional layer, filters. And in this second convolutional layer, filters. So it's just arbitrarily saying it's going to be the same size. Dropout is given here, but it's fixed amount. But for the dense layers, we're going to supply a list. So this is going to get interesting. Because it's like, well, you could provide more dense layers. What this sequence is going to do is make a new model that's sequential. It's going to add a convolutional layer to that model. Filters is how many sets of weights we're going to have, I believe. Let me super double check that. Conv duty. Convolutional kernels can evolve layer, yada 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 yada. Integer, the dimensionality of the output space. Yes. Number of output filters. Yes. Whereas kernel size is integer or tuple list of 2 integers. Yes. So that's the number of sets of weights that we have. Question from the audience: why do you normalize? I would say empirically, it's been shown that if you normalize the inputs to your model, and especially if you renormalize after each layer, you can, yes, as you say, keep your gradient from getting out of control, and it tends to work better. If you're doing just linear modeling, don't even worry about it. That should not really be an issue. It's a computational issue, not a mathematical issue in a sense. We're getting burned sort of by the precision of our universe. Okay. So yes, so you add a convolutional layer. You're going to put an activation on this. This is the function that you put your weighted sums through. Rectified linear. For those of you who don't know, rectified linear, god damn it. Do not know why. Alright, I don't know why that's not working. Anyway, rectified linear looks roughly like this, strangely enough. Yeah, that's so weird. So if the value is below 0 or below, it's 0, and if it's above 0, it's just linear, as in it's the identity, in general. That's why it's called rectified, but still linear. So, we're saying the padding here is valid. So, given your input image of 28 by 28, I believe this means if you slide your window over, and it goes beyond the edge of your image. If you say padding equals valid, you say, don't bother, don't do anything. So you're going to lose a window, the size will decrease. Whereas if you say padding equals same, you'll put in some dummy value when you're over the image. And so you can get the same input shape out. And this final input shape, this is just to tell Keras, hey, I'm putting in this 28 by 28 image for each data point. Let's see, we did the activation. This is just a second convolutional layer, but note now it's working on the output of the previous convolution. So it's going to have whatever number of filters here, channels to work with, whereas the first one had 1 channel to work with. But now we've effectively created like 10 sets of images of the same size. And the image will be a slightly different size too, because we're doing this valid padding, depending on the kernel size. The kernel size is, remember, how big that window is. Okay, but you do another convolutional layer, you get 2 of them, and then you do another activation, and then after both of those, you'll do this max pooling. So you'll look at each 2 by 2 window, and you'll decide, of this 2 by 2 window, which is the largest value of the output of the activation, remember. You'll say, keep that one, get rid of the rest. After doing that, finally, you say, okay, during training, randomly pick 25% of the nodes for a given batch, just zero them out. Just ignore them. Don't consider them. We're not going to train them those nodes at all. And so the other nodes will have to pick up the slack. This helps fight overfitting and helps generalize the model a little bit. Okay, after we've done that, we've set some sort of image shape that you still have to contend with, which can be frustrating to deal with. You no longer really care about the structure. You've sort of extracted all the interesting structural features. So now we want to flatten it out and get a nice one-dimensional array for a given data point. Finally, this part's pretty interesting. Dense layer sizes is going to be a list of layer sizes. So it might be, oh, I want to compute 10 things, and then 20 things, and then 30 things. And so this first layer gets the output of the convolutions, flattened a whole bunch, and every one of those weights will be used to compute 10 new values. And then those 10 values will go through some nonlinear recombination with the dense layer and used to compute 20 values. And note that we don't pass in activation here. I believe that comes with a default activation of sigmoid. If you don't, is that true, or is it linear? Activation equals none. Well, deactivation is an element-wise, yada yada yada. If the activation is none, if you don't specify anything, no activation is applied. Well, that's just linear then. So if you compute 10 things linearly, then 20 things, then 30 things, that's really just the same as computing 30 things in a linear world. You can just always find a recombination of weights to make that work. So I'm curious if this is correct. This might not be doing anything different. It might only depend on the final layer size. And maybe that's what it's designed to show. This list has one number for each layer. Yeah, for each layer. Yeah, you might just be doing more computation than is necessary. If you did this, if you had an activation after each one, then yes, it's nonlinear. You can't just recombine them with a simple sum. But that's not the way it's written here. So anyway, you're going to do your dense layers. I'm suspicious that it's doing the correct thing. And then you do this rel-u activation after all that, so put it through a nonlinear function. Half of those, whatever the last size of your layers is, if it was 30, over here, whatever the last size was, during training, get rid of half of them. Just gone, poof, not worried about it. And then finally you have one last dense layer. This is computing your final outputs. So num classes, you compute 10 different things. And those 10 things you put through this softmax activation to take those 10 values, which are real values that are positive or negative, or I guess they're all going to be positive because they're rel-u, but it's going to take those 10 values and squish them into a probability distribution. So you've got a certain probability class 1, class 2, class 3, etc., and they will all sum up to 1. They will all be positive. They will all be between 0 and 1. And that's just about it. Oh, okay. And well, you got to given a model that you've done, you need to compile the model in Keras, which just tells it how are we actually going to train this model. So first you need to tell it what is the score that you want to climb on. And for us, that's categorical cross entropy. And this is briefly what I was describing. This is our target. This is the sort of probability distribution we would like to reach. If your computed probability is like 0.1, 0.05, 0, 0, 0, 0.9, 0, comma 0, whatever. We've got this 0.9 in the position where the 1 is. So all you're going to do is dot this vector with this vector. Because this is mostly zeros, it has the effect of just giving you the value of whatever the correct position probability is. There's a little bit more involved in it, but for our purposes, that is enough to understand. The optimizer we're using is called eta delta, which the eta is for adaptive. An adaptive delta, the adaptive change in something. I don't know exactly what eta delta computes. You can also use, for example, SGD for stochastic gradient descent. You can use atom. You can use RMS prop. I find that that's something that one tends to discover empirically for any given model. So that could be another like grid space you could try. Oh, try different optimizers on your grid search. Oh well. Another question from the audience: how do you get confidence interval or uncertainty measure with the class predictions? I just sit down and think about that real hard. That's based on the like final logistic regression output. So you do get a probability, but your question is how sensitive are those probabilities to sort of the input, or how confident are you in them? Yeah, I'd have to sit down and think about that. I can't, off the top of my head, I can't say, oh, you definitely just do X. Okay, let me run this model, and I'm going to delete a couple lines just because I'm empty lines, so I can do this interactively. But other than that, it is what it is. And if it looks like I'm running out of time, I will pick up the pace. But I like going through explicitly. Give it a little more space here. Okay, dense size candidates. So these are the sizes of dense layers we're willing to consider. As I said, so it's a single dense layer of size 32, a single dense layer computing 64 values, or two dense layers each computing 32, or two dense layers each computing 64. That's all. And again, I'm suspicious that we cannot just, that these two-layer versions have any chance of being better. I am very suspicious. But we'll see what it is. So we've only got 4 possibilities. All right, our classifier is using this make model function. So make model creates the entire model object. And apparently that's what Keras classifier, this wrapper around sklearn, wants. It says, given these parameters, give me the model. And we pass in the batch size to Keras classifier. So how many data points do you look at once when you're recomputing the weights? When you're training the weights, I should say. So we can just make that, I guess. Okay. Let's have a look-see at this validator object. This is the grid search CV, the exhaust over my parameters. So first, you pass in whatever your model constructor is. So for us, it's this Keras classifier object. It might be something like logistic regression or linear regression otherwise. Then you define your grid. What are the things that we want to exhaust over? Oh, epochs is on here. Okay, so this must be some built-in to Keras classifier that we didn't actually look at. But the number of training epochs is something that you can also exhaust over, but it's not built into the make model. Okay, so param grid, the things you can exhaust over. So dense layer size candidates, that we went over just a second ago, up here. Eval is available for tuning even when not in arguments and model building function. Oh, okay, cool. The filters. This is sort of how many different sets of weights we compute on the convolution. We're just only going to look at 8 here. That's it. Kernel size, we're only going to look at 3x3 windows. That's it. Pool size, we're only looking at 2x2 convolutions. So, we've only got, in fact, 4 things here that we're going to look at times 2 things here. All these letters are 1, so it's like times 1. So we've got 4 times 2 times 1 times 1 times 1. Yes, we got that many things. So there's 8. 8 different models that we're going to build if you want to exhaust everything. Scoring is negative log loss, which should be equivalent to our cross entropy. Or like that's what our model is going to report, I believe. Not 100% sure on that. And njobs equals 1 is how many CPUs we want to spread this over. Or not CPUs, I guess, because we'll be computing on the GPU. So we don't want our jobs to clobber each other in the GPU, so we're going to say 1. If you just had a CPU-based model or access to multiple GPUs, you could bump this number up to however many of those you have. So let's specify this. I've never used this thing before. This is cool. And like running lots and lots of models is to find the best one is something I do. Okay, and then in Keras, as in scikit-learn, the way you create a model, the way you train a model is say whatever .fit, and you pass in what is my input training data, and what is my desired output training data. And this validator object works the same way. So this should train 4 models. Neg log loss is not a valid scoring value. Valid options are. Interesting. Well, that's funny. So that's something that perhaps scikit-learn. I don't have a new enough version or what, but that's fine. I wish it would have yelled at me when I created this. Part 2, recall weights. These are all various classification kind of things. Oh, I bet CV is like for classification. Is that true? Fit and score. Note from the audience, grid search performs badly with neural nets, mainly due to a number of hyperparameters that can grow exponentially. Well, I don't want to say that the grid search performs badly, it's just there's no way you can finish the grid search for a reasonable size grid. And this really, like, you'd want a lot more possibilities for the dense size layer, you'd want a lot more possibilities here. And yes, as noted, it grows huge. Suggestion is to use random search or Bayesian optimization. There are possibilities. I'm a fan of using the genetic algorithm. And that's non-trivial to do, and I'm working on some research related to that. That will, hopefully, one day I'll be able to like demonstrate. But that's what I use. So I train a couple different neural nets, and then I mix and match pieces between them, the ones that work well. So we have changed negative log loss to just log loss. We'll see what happens. I might change it to like accuracy or something, just to be for giggles. So this should take, it's got to compute 8 different models, but they're MNIST, and it's only training for up to 6 epochs. So it really shouldn't take that long. But there's no progress bar in sklearn. That's one of the best parts about Keras. You get a progress bar. It's so nice. And so the Keras classifier object is going to be taking care of a lot of the mishmash between the sklearn validator or the grid search CV and how the Keras model wants to train. But it's super good that you can just pass in epochs too. I like that. Let's see, did I miss any other questions in here? There's discussion, is it better to use maxpool than RelU or RelU than maxpool? That's an interesting question. I think RelU than maxpool. But it really, if your activation function is monotonic, it doesn't matter. Yeah, it's not going to make a difference what you're doing. So you might as well max pool first, I guess, because that's faster. Because it saves you some nonlinear computations. Oh, now it's going. All right, so it just had to, it took forever to initialize the model. So you do get to see your training. So this is actually super cool. It just takes forever to compile. As is always my problem. I wish I could pre-compile these models. Because when you say compile, it does not actually compile in the sense that you are used to in a software engineering world. It does not convert your Keras code to machine code. That doesn't happen until the first time you actually try to train or run your model, which saves a little bit of headache. Okay, so that's the first model. It's going to take 3 epochs. I kind of wish I had given it fewer of these now. Yeah, so I am in fact going to do that. I'm going to consider a smaller guy. Because ain't nobody got time for this. I mean, this is taking a minute. And this is probably on the smallest guy. This is probably 32 and 3 epochs. And we still got to do 32 and 6 epochs. That's going to take forever. Ain't nobody got time for that. Nobody. Nobody. I seriously had no idea this was going to take this long. I'm going to change this to like 1 and 2, I think, too. In fact, let me interrupt this. So I'm going to consider a smaller size There we go. So now there will only be 4 models to consider. I will train one for one epoch. I will train the other for 2 epochs. It will still take forever to compile. The nature of the beast. Alright, while that thinks about it, once you get the correct answer, this validator object is going to hold some of your interesting parameters to include what is the one that gave me the best score. So it's going to have, probably for each one of these keys, it'll give you the value that had the best score out of all of them. And I would not be surprised if you had all the scores from all the combinations, depending how large a set is. So sklearn best estimator, this contains the scikit-learn wrapped version of your model. So it might be a pain to use, but if you just say .model, that's the actual Keras object of the model. So you can do all the usual Keras things you can do to it. So here, you pull out the model. Here, you pull out the names of the various metrics. So I'm guessing that's like the log loss here. And metric values, you're saying evaluate. So how good is the best model as trained on the training data with the testing data? And then what do we do here? And then we compute just what are all the metrics that we have. Alright, okay, I see. For all the metrics that we're considering, which is apparently, I thought it was just log loss, but it could be a whole lot of things. Who knew? And then you just print out, essentially you print out that dictionary for this model. And you say, okay, for this metric, log loss, this model did this well. For this other metric, accuracy or whatever, did this well. For this other metric, F1 score, did this well. Whatever all the student handy stuff is. But yes, this is grid search. There's other ways to do it. But this is good to know. I mean, if you don't have that many sets of parameters, and you can parallelize over multiple CPUs or GPUs, like this could save you a lot of headache. Rather than setting up, 10 lines of, rather than like even writing a function to do it and setting up those, 16, however many lines you got to work with that you got to deal with. This just says, run them all and do it, get back to me with the right answer. So that's cool. I didn't know about this. And I'm super cool that it's here. And I was fully expecting this to be quicker to go through. But you know what? Taking your time to walk through slowly a given model, that just takes a long time. Is this training on the test set? Why is this 20,000? There's not 20,000 testing things, are there? I don't even get, no, it doesn't, it has no access to the testing. What is 20,000, man? I have no idea. Epic 1 of 1. I seriously have no idea why there's 20,000 listed there. That's not how many data points there are. Oh, I see. It's splitting up. There's 60,000 training data points, right? It's saying use 2/3 of them, 40K, to train this model and score this model within the grid search on the last 20K. This has got to be a parameter to grid search CV or something as far as how much you can use. That has to be what it is, because that makes sense. Because otherwise you're choosing your grid search, whichever one whichever model most overtrained on the training data, it would obviously perform the best on the training data. So that's why you hold back some of your data, this 20K. Even though it's part of your nominal training data set. You hold it back there, see how it does, and then you use that to decide, use that withheld data to decide which of my grid search models is the best. And finally, use the best grid search model to see, all right, how does it do on actual test data? Because in effect, you're climbing your grid search model on this withheld data, these 20K withheld data points. And we're getting the progress bars because of the verbose mode equals 1 inside the evaluate? Probably. I like verbose, but no, I love progress bars. Progress bars are so good. I cannot get by without progress bars. Too good. This might be a little too much verbose. That is a possibility. Oh, this takes forever. So even for MNIST, I did not think one epoch was supposed to take 45 seconds. I thought it was supposed to take, I guess it is a convolutional model. That does take a little longer. There's just a lot of computation involved. You have fewer parameters. And it's often like correct, it's a pattern recognition kind of thing. Alright, let me kill some of these guys. Discard. There we go. Discard. I don't know what's up with the GIMP. It's being silly. So, as I said, that was just one of these, this MNIST sklearn wrapper, just as an example. And the fancy business there is really this Keras classifier object. That's really what the cool part there that Keras really provides. The rest of this was just sort of dressing to make all that work nice. Other things that I think might be good to look at, Reuters sounds cool. Let's look at that. Or Keras contrib, someone asked about. Keras contrib. If I can spell correctly. Here we go. So examples in Keras contrib. There's only a few here. I was expecting more. What is this? Improved wide generative adversarial network. Determine the loss function with penalizes such and such, such and such. Weiserstein loss. This has a lot of good text right there. Simple model. Interesting. I thought there'd be more. Is there more inside here? There is not necessary. So Keras contrib, for those that don't know, is sort of community contributed extra code. So it might be do activation functions, new types of layers, all kinds of other stuff. Someone wants to look at the DenseNet FCN. Is that in the examples? DenseNet? Fully trains DenseNet 4012 model. Okay. It's 94.84% accuracy score after 100 efforts. On Sci-Fi 10, that's not bad. I've trained some crummy models on Sci-Fi 10, let me tell you. I've done pretty terrible. So, DenseNet, create a model without loading weights. Just interesting, okay. So it just creates the model and then walks through it. Yeah, so it implements its DenseNet object. Yes, Keras contrib activations, DenseNet, and then uses it. So the rest of it is really just set up for how to do Sci-Fi. So, really you're asking, how does DenseNet work, perhaps? Keras contrib, that was what, under layers? Applications, excuse me. DenseNet. Densely connected convolutional networks. Those seem like two oddly different, diametrically opposed things. Fully convolutional dense nets for semantic segmentations. Interesting. So maybe I can take a look at that. I'd have to read up and like, what the heck is DenseNet? Because there's a lot of extra stuff here. That's looking complicated. Maybe I'll walk through it. But walking through 600 lines takes a little more time, is a little more complicated than walking through, I don't know, the 100 lines of this file. And training with Sci-Fi takes a lot longer than training with MNIST. There's just more data, the data files are much bigger. They figure they're a little over, it's 32 by 32, which is like 1,000 times 3 channels for the red, green, blue. Yeah, which is like 4 times the size of MNIST, just in terms of the data input size. And so you need and you're computing, you still 10 probabilities you're computing. You're trying to figure out 10 different classes of objects that are like car, plane, deer, something ridiculous like that. Oh well. So maybe I'll take a look at that next time. Maybe I'll just work through the not how does DenseNet work, but I'll just work through the example. That's an entirely reasonable thing. Which just sets up Sci-Far 10, calls DenseNet, and trains it. Yeah, that doesn't look too bad. Depth, NB, dense, growth rate. Yeah, not 100% sure how these things work. This is almost done. It's almost done. We're almost, the grid search is almost there. Almost. Problem is it takes 46 seconds to train and then like another 23 seconds to validate. Even though I don't really need the validation accuracy after every epoch. It's almost there. We will finish it. We'll finish before the hour is up. We'll almost have that. So yes, leave a comment or send me an email if you've got a particular file you'd like me to work through, such as this DenseNet thing, or one of the official Keras examples. That would be interesting too. Like, I don't know. I just happen to click this Reuters MLP because I suspect it's on text and it's not that bad to look through. I might be totally wrong. You never know. Because it's got 512, which is kind of big, you know. But why not? You know, why not a million? Why not a million nodes? I don't know. That's what I'm curious to see. Like, if someone builds hugely wide nets, how do those perform? All right, we're almost through. Last bit of the last epoch of this silly model. We will have done 4 models, scoring on the log laws for whatever that means. We only really have 2 dimensions: how big is our dense neural layer, and how many epochs are we training. And you're going to learn that training 2 epochs with probably the larger size model gives better results. Big surprise. 81 versus 86. Yeah, probably. I can see that here. Ugh. Any type of fully convolutional network. Huh. Yeah, I haven't checked out fully convolutional network stuff before, so maybe I'll take a look at that. And I did not know about this sklearn grid search. I didn't know about this sklearn model selection thing. I might have to take a closer look at this. Hyperparameter optimizations, randomized search, grid search, fit grid point, run fit on one set of parameters, model validation. Yeah, I might have to try these things out. Discrete number of values for each. I'm definitely going to try some of these out. This might save a considerable amount of headache on just, oh, try this, try that, try this other thing. I don't know what works. See if this is better. Like, set it running and forget about it. What? There's another one? No, you were the chosen one. You were only supposed to do 1 epoch and then 1 epoch, and then I thought that was all 4. There should only be 4. 4 different models. Why? Why are you training another one? Fine. Yeah, it has no attribute best params because it never finished because it was silly. Dot estimator decision function CV score all kinds of stuff. All right, so I was too impatient and I thought I was doing more work than I should have, so it did not finish. But that's okay. We worked through how all these things actually would work. And you know what? That's the problem when you're trying lots of different kinds of models. It takes a long time to figure out what is the right kind of model to use. So set this going, go out to lunch, take a break, come back later, and then see how it's doing. Okay, I think that is all I got for tonight, so I want to thank everyone for coming out. My voice is really shot, and I appreciate all the ideas, thoughts, comments in the chat. You guys really help make this more fun for me. So, that's it. Have a good night. Don't forget, stay safe in the data mines. Thank you.